Forest Department, ICFRE, CTDT, Anna University, and SSN Trust. He also completed one international bilateral project during 2020. Dr. Gulam has generated revenue worth of rupees 9.16 lakhs through consultancy activities at SSN College. To his credit, he has two granted US patents and 18 Indian patents. Further, he has filtered 10 other patents which are currently under examination. He has authored and co-authored 140 plus research articles on antenna and microwave components in leading international journals, including IEEE Transaction on Antennas and Propagation, IEEE Transactions on Vehicular Technology, IEEE Antennas and Wireless Propagation Letters, etc. He has also presented and published his research paper in 50 plus proceedings of international and national conference. He is listed in World Top 2% Author Database 2021, 2023, and 2024, compiled by Stanford University for Elsevier based on research publication. He is a recipient of Best Researcher Award 2024, Outstanding IPR Award 2024, Publication Excellency Award 2019 and 2021, Teachers Par Excellency Award 2019, 2020, 2021. Dr. Kula has organized several FDP and SDTPs funded by Anna University, IEEE, AACTE, and SSN Trust, and has also organized an international conference at Anna University and a national conference. As on 2024, Dr. Gulam has delivered 60 plus invited talks in various engineering colleges in India. It is our pleasure to have you a resource person for this session at NPSB CET. A warm welcome to you, sir. Welcome you, sir.
Thank you.
Thank you so much, ma'am, for the introduction.
Yeah. Thank you, ma'am. I once again welcome our respected resource person, Dr. M. Ghulam Nabi Azad, and all the participants for joining our ATAL FDP program. Sir, shall we start the session, sir?
Yes, ma'am. Shall I share my screen?
Yeah, you can share, sir.
Yes, ma'am. I'm sharing the entire screen, ma'am.
Yes, sir, your screen is visible.
Yeah, so I hope the presentation is also visible.
Yeah, it is visible, sir. It's visible.
Yes. Yeah, okay. So, good evening, all. So, foremost, I extend my sincere thanks to the organizers for having me here. So, the ATAL FDP is about Industry 4.0, where the FDP covers several aspects, and one of the aspects was wireless communications. So, I basically work on antennas domain. So, I'm here to present my research and my activities with respect to the next generation wireless communication from the antennas perspective. So, to be precise, we are actually talking about sixth generation. We are currently exploring the possibilities of having wireless communications in 5G, and now we are exploring the opportunities in 6G, and now the evolution will continue. So from 2G to 3G, from 3G to 4G, and 4G to 5G, and tomorrow 6G. What we are actually looking for is enhanced bandwidth. So if the bandwidth is more, then you can have a higher data rate. And if you have higher data rate, then you can have seamless communication. So from the start till the end, if you can enjoy your information entertainment system, there lies the success of wireless communication. So people are trying to continuously work on the methodologies, and research is on foot to find the best ways to establish good communication between the transmitter and the receiver. Now, in line with this, various researchers are focusing on several aspects of wireless communication. Right from the signal processing side, the modulation type, how to handle complex environment, how to mitigate the fading effects, how to overcome the effects of large scale scatterers. All these are different perspectives with which people work on. And there were several technologies like cooperative communication, relaying methods. And we have this NOMA, which has been currently spoken of. All these are variety of signal processing techniques that are used to improve the communication. But behind all these things, there is one important entity that is required, which is antennas, to establish a successful communication between transmitter and receiver. So since I have largely worked on antennas domain, I thought it would be perfect to talk about how antennas are evolving in the next generation. Again, antennas are no entity which can transmit and receive electromagnetic waves. And in the sixth generation, the antennas are seeing a new perspective, which is the intelligent reflecting surfaces. Now, this intelligent reflecting surface is a meta surface, and this meta surface can be used to establish a communication if in case there is an obstacle between the transmitter and the receiver. Now, theoretically, people have investigated the different types of intelligent reflecting surfaces, but only a few people have demonstrated practically. Now, what we will be discussing today is that the intelligent reflecting surface, but not exactly on the topic of intelligent reflecting surface, but on the topic of reflector array antennas. Because a strong foundation on reflector array antennas will help one to understand how these intelligent reflecting surfaces can be constructed for sixth generation communication. So moving forward. So this is my outline for today's presentation. Any presentation, I'll always start with some fundamentals so that everybody can understand. So I'll throw a few important aspects of antennas, and we will directly get into high gain antennas, wherein we'll talk about reflector array antennas, which falls under the category of spatially fed array antennas. And this array antennas, reflector array antennas, when I discuss, I'll try to map it with the intelligent reflecting surface so that one will be able to understand how to design intelligent reflecting surface by understanding the operating mechanism of reflector array antennas. So to make one understand how these surfaces are constructed, I have taken some literature on reflector array antennas, and I'll also help you to understand two different reflector array antennas which are developed by me in our laboratory. So to begin with the fundamentals, so everybody knows what antennas are. So any piece of conductor, when it is connected to an oscillating source, the electrons, they oscillate and they create radiation. And this radiation is very essential for one to establish communication between the transmitter and the receiver. According to IEEE's definition, antenna is the means by which one can radiate or receive radio waves. Not only radio waves, now today we are talking about microwaves, millimeter waves, and even people are working on the development of antennas which can work in the terahertz frequency range. So it is the one that connects the electronic circuit with the free space by transmitting energy from the electronics to the free space and capturing energy from free space to the receiver. And without antennas, the communication is dead. So it forms an integral part of any of the wireless communications that we see presently. The block diagram below depicts how the antennas are utilized at the transmitter and the receiver. So basically, antennas are reciprocal in nature, which means that if you connect the antennas to the transmitter end, it will just convert voltage current into electromagnetic waves. On the other side, if it is on the receiver, it will collect all those electromagnetic waves, convert them back into voltage and current. So basically, antennas are transducers. They just convert voltage current into electromagnetic waves and vice versa. And now we see a variety of antennas in our day-to-day life. Now all these antennas have taken a definite shape and definite size based on the radiation principles. Sometimes the communication has to be established in the terrestrial region, and sometimes it should be a point-to-point communication. So based on the user's requirement, the radiation pattern of the antenna has to be shaped. And for shaping this antenna, one has to create, or one has to go with some kind of a form by which the antenna can create radiation in the desired direction. Say, for example, if you look at the antenna in E, so everybody should be knowing this antenna, which is the monopole antenna. So this particular monopole antenna, it radiates everywhere. It radiates around itself. So if you see this antenna, it is connected to the router. So anybody is in close proximity to this router, they get immediately sensed, and they get connected to the internet. So that's a kind of a radiation which this particular antenna is throwing out. Whereas if you look at C or D, they are parabolic dish antennas, they are high gain antennas, and these antennas are used to establish communication with objects which are at the farther point. Say, for example, I want to do a satellite communication. I want to do a Mars mission, lunar mission, right? A Venus mission. For all these kind of long distance communications, you might require high gain antennas. So C and D are directional radiators which can cover larger distance. So all these antennas have their geometry to meet certain purpose, right? But all these are antennas. They serve only one purpose, which means that if it is connected to the transmitter, it will radiate energy. And if it is connected to the receiver, it will capture energy from free space and convert those energy into voltage and current. Accordingly, antennas can be classified into three major types, which is broadly said as simple antennas, complex antennas, and array antennas. Now, before that, the size of the antenna. So now we look at our present day smartphone. Our present day smartphone is fitted with numerous information and entertainment system. For example, the antenna has got no GSM application. There is GPS. There is Bluetooth. There is Wi-Fi connectivity, and there is FM, and there are so many other things that uses some portion of the electromagnetic spectrum. Now, all these variety of applications do not operate in the same frequency range. They operate at different frequency range, occupying different portions of the electromagnetic spectrum. So it means that every application might necessitate different antennas. But all these antennas are put into one single package, and you see that the package is not too huge. It is so compact that you can accommodate the entire device into your palm. Now, how this has happened? Because all these applications have been driven from low frequency to high frequency. If you look at the classical communication, we had AM, FM. Now we have moved to data services, and we're still enjoying the music right without any interruption. The thing is that when you were in AM and FM regime, you were operating at the megahertz scale, and now when you migrated to data services, now you're operating in the microwave frequency band. Now, because of this migration, what has happened is your frequency has increased, and because your frequency has increased, the bandwidth has increased. Because the bandwidth has increased, the data rate has increased, and once again, because the frequency has increased, the wavelength has decreased. Now, the wavelength is related to the electrical size of the device. Now, what has happened is you have increased the operating frequency. Therefore, no wavelength is inversely proportional to frequency, and therefore the wavelength has come down. The electrical size of any entity, any circuit is given in terms of lambda, and automatically this electrical size has also come down. So one way to reduce the size of any device is to operate at higher frequency. Likewise, your antennas are also made smaller, made miniaturized by operating at higher frequency. So by working with the higher frequency region, you can reduce the size of the radiator. And as I told you, the shape of the antenna depends on the type of application for which it is intended for. As said, sometimes you might require terrestrial coverage, or sometimes you might require point-to-point coverage. Accordingly, what happens? The shape of the antenna is dictated, right? So as told to you, broadly, it is classified into simple antennas. Simple antennas are those antennas which can be easily understood by any common man, right? All these wire kind of antennas are example for simple antennas. On the other hand, all aperture type of antennas, we call it as complex antennas, or even the Yagi is said to be a complex antenna, because one cannot easily decode how this antenna is functioning. Say, for example, if you look at the Yagi antenna, so it is basically used for terrestrial television communication. It has got a driven element, which is basically a folded dipole. It also has a set of directors and one reflector. Now, all these are aligned in such a way that the antenna produces a unidirectional radiation pattern. Now, common men cannot quickly able to judge how this has happened. So such antennas are called as complex antennas. And if you look at antennas like horn antennas, which can typically have communication up to a few kilometers, right? Now, what happens is that the current distribution within the antenna's aperture is very complex. So it is not easily decodable by a layman. So such complicated antennas, we call them as complex antennas. And sometimes when the distance to be covered is very, very large, then one antenna might not be sufficient. In this case, what you have to do is you have to deploy more number of antennas, and we call that as phased array antennas or simply array antennas. So array antennas are collection of antenna elements that gives a very large directivity. And if the antenna is made beam steerable, then I might call that antenna as a phased array antenna. So let it be a simple antenna or a complex antenna or a combination of identical antennas. All these antennas do the same job, which means they convert electromagnetic waves into voltage and current if it's a receiver, or it captures or it converts voltage current to electromagnetic waves if it is a receiver. Right? So that's a job. So the transmitter antenna transmits energy that is radiates maximum energy into the surroundings, whereas the receiver antenna captures the maximum energy from the surrounding and gives electronic circuitry. So these are some of the important antenna related parameters. So any antenna designer might be doing this. So when you choose an antenna, you must know for what frequency this antenna is operating. The frequency depends on the type of application. Like I said, 5G. So 5G has got two frequency ranges, FR1 and FR2. So we are actually exploring the benefits of FR1. We are not actually exploring the real benefits of 5G, which lies at FR2. So I told you, right? So whenever you evolve in the communication generation, you actually raise your bar in the frequency. Like the classical communication AM, FM, it operated in the radio frequency range, and then we migrated from radio frequency to microwave frequency. We are still in the microwave frequency range, where no, in even in 5G, we're exploring the opportunities in the sub 6 gigahertz band, and we are trying to exploit the maximum utility of 5G in the millimeter wave spectrum, which demands a lot of infrastructural change both at the handset and at the base station level, right? So what happens at the FR2 range, the antennas that are used for transmission and reception, they're basically array kind of antennas, right? Means that these antennas will exhibit a very directional radiation pattern. So currently what we are doing is we are exploring FR1 frequency range where the antennas are having omnidirectional coverage, right? Whereas if you go to the FR2 range of 5G, the antenna radiation pattern is directional, and these antennas are steerable so that you can lock onto a particular base station, thereby maximizing the link reliability, right? And similarly, if you look at the handset, your handset will come out with many number of antennas, making a pretty MIMO kind of a scenario, so that no, you establish communication in different orientations of the mobile handset as well. And you all may be aware that we may not be always having the mobile phone in one specific orientation. Sometimes it will be in the landscape mode, sometimes it will be in the portrait mode, or sometimes you'll keep it no inside your pant pocket, or sometimes on your no shirt pocket. No, the orientation of the antenna changes with respect to time, right? But these orientations should not affect my connectivity with the base station, right? So when you use a directional radiator, automatically what happens is that there is a possibility that you might lose your link with respect to the base station. That's why in the FR2 range, people try to use MIMO scenario so that you overcome the disadvantages of orientation. No, that's a real benefit there. But no, this requires a massive massive changes at the infrastructure level, both at the handset as well as at the base station, which people have not done. And specifically for a country like India, where there's a huge population, more number of mobile users, it's very difficult. So people are trying to explore the possibility of implementing FR2 5G frequencies, right? So now frequency becomes so important. Now, as I told you in the very beginning itself, our focus will lie on sixth generation. When I talk about sixth generation, now people are trying to exploit the zero point 0.1 terahertz to 10 terahertz frequency regime, which is a non-ionizing radiation, radiation in the electromagnetic spectrum. Now, what happens in that particular range? What are the atmospheric losses? Now, how these losses will be overcome by the new technology? All these are studies that have to be made, right? So, because spectrum allocation is not done at the sixth, in the sixth generation, we are trying to see which part of the electromagnetic spectrum between 0.1 terahertz to 10 terahertz will be very much useful to me, right? So it's a standard. So the standard will dictate the frequency, right? So any antenna that you design should have a definite frequency with which it has to operate. And then the next important thing is the input impedance. As I told you, antennas are not standalone entity. It works with an electronics. The electronics could be a transmitter electronics or a receiver electronics. The electronics will have its own impedance, and antenna has to be coupled to this electronics. So whenever the electronics impedance and antenna's impedance are matching, then there is a possibility of radiation. But when the coupling is not so good, the antenna might not radiate well. Therefore, the impedance also becomes an important matter. And if you compromise on the impedance value, automatically you end up having a poor VSWR. So you have to ensure that the voltage standing wave ratio is better. And the next important agenda is bandwidth. As I told you, any wireless communication will operate the fixed bandwidth. Say, for example, I have a router. The router is capable of dual frequencies. It works at 2.4 gigahertz. It works at 5 gigahertz. Suppose my modem's antenna is broken. Now that has to be replaced. Now, what I do if I replace the antenna with a single operating band, right? The benefits of the modem cannot be obtained fully, which means that the modem is capable of operating at 2.45 gigahertz and 5 gigahertz, but the antenna that is connected to the electronics can work only at 2.45 gigahertz. Now, all these 5 gigahertz benefits are lost, right? So, you should be knowing at what frequency the antenna is operating. Now, what is the bandwidth that is required by the electronic system? Is my bandwidth requirement is getting satisfied? All these things one has to evaluate. And the next important thing is the polarization. We all know that polarization means the orientation of the electric field vector along the direction of wave propagation. So whenever the polarization is matching, then there is a maximum coupling between the transmitter and the receiver antennas. And whenever there is a depolarization, automatically you will end up losing most of the signals, right? Now consider a scenario, a complex scenario where there are a lot of scatterers, right? Now there is a base station which is transmitting energy with vertical polarization, right? Vertical polarization. But because of this scattering effect, because of this large scale scatters that are present, because of the environmental clutters that are present, now this vertically oriented electric field turns its polarization from vertical to horizontal. Now you have a receiver. The receiver is vertically polarized. But all these signals which are depolarized to horizontal will reach the receiver. Unfortunately, the receiver is vertically polarized and no, it cannot capture the information in the horizontal polarization, right? So whenever there's a mismatch in polarization, you might be losing some information. Therefore, one has to ensure the polarization with which the antenna is supposed to work, right? And then comes the beamwidth. As said, sometimes the coverage requirement is so large, you have to cover no a lot of area, or sometimes you have to cover no a smaller area. Sometimes it is a point-to-point communication. So depending upon that, one has to shape the radiation pattern, and that will say how much the beamwidth of the antenna should be. And the last important one, which any fundamental any beginner has to understand, is the gain of the antenna. No, this is not the amplifier gain. So whenever we talk about amplifier gain, you give no some input and you get a large output, right? So this is not that gain. The gain here is about the ability of the antenna to transmit or receive more information compared to a reference antenna. Many times this reference antenna is an isotropic radiator. So isotropic means it radiates equally in all the direction. So if you look at the radiation pattern of an isotropic radiator, it typically looks like a sphere. It's a spherical ball, right? The radiation looks like a spherical ball, which means that if you have a spherical ball, the spherical ball could be characterized by latitudes and longitudes, right? As we have in our planetary system, right? There are horizontal circles and vertical circles, which are characterized by the elevation angles and the azimuth angles, right? So it radiates equally everywhere. But if you look at directionality of an antenna, it will radiate energy in a particular portion of the particular portion and not everywhere, right? So when you compare the gain of your antenna with an isotropic radiator, you can understand how much more it can transmit or receive information compared to an isotropic radiator. For example, the isotropic radiator has a gain of 0 dB because it radiates equally everywhere. The gain is equal to unity. In logarithmic scale, it is 0 dB. I have an antenna with no directionality, with more directionality, whose gain along a particular direction is 20 dB, which means that I can express the gain of this antenna as 20 dBi, which means that this antenna which I am talking about no, can transmit or receive, it can radiate or receive signals 20 dB higher than the isotropic radiator, right? So that's the importance of gain. So the gain depends on the coverage distance that one has to cover. So if the coverage is very large, then the gain requirement is also very huge. For example, I'm doing a moon mission, a lunar mission, right? Just imagine the distance. Suppose I'm doing a Venus mission. Just imagine the distance. Suppose I'm doing a mission with respect to Mars. Just imagine the distance. But the distance is different. The coverage distance is different. Accordingly, the gain requirement is also different. So at such scenarios, what people will do is they will use high gain antennas, right? And no, high gain antennas are realized using antenna arrays, and these arrays will have more number of elements depending upon the coverage, right? Say for example, if the coverage is going to be several thousands of kilometers, then I might require more number of antennas participating in the radiation process, which for in my case, no, if I try to do a reflector array antenna for that particular application, the reflector array might demand more than thousands of elements to be printed, so that no, I will be realizing such huge gain, right? So these are some of the fundamental parameters that one has to remember. So, as I told you, we are talking about next generation communication, right? The 5G and 6G. All that we are looking for is higher data rate, better link reliability, lesser error, good bandwidth, global connectivity, and minimum installation cost and structural complexity, right? As I told you, once again, when you migrate from 5G to 6G, you are going to migrate from one frequency range to another frequency range. That is, you will be at no, you are currently working at microwave in 5G FR1, and no, you're trying to explore the opportunities in millimeter wave, that is beyond 24 gigahertz and up to no 70 or 77 gigahertz. And now no, you try to move from no millimeter waves to terahertz frequency range, where you will try to explore the opportunity present in 0.1 terahertz, that is 100 gigahertz to no 10 terahertz, right? So when you try to know work at higher frequencies, automatically new engineering problems will arise in terms of the materials and methods. See, antennas are constructed using dielectric materials and conductors. Now we have to look at the loss performance of those materials at such high frequencies. Accordingly, you might be discarding some materials which might not be working so well at high frequencies, right? So careful choice of materials are required for the development of the antenna. At the same time, can you use conventional methods for realization? See, I cannot create a dipole antenna that can operate at such high frequencies, right? Because it might not give me so good gain that one is looking for. So when you want more gain, automatically you have to adopt new methodology, so that no, you overcome the hurdles of the conventional radiator and you arrive at the development of a new radiator, right? That meets the requirement at such large frequency, right? And no, again, when you go to higher frequency scale, see, any antenna, anything that you develop, may it be an electronic component or an antenna, right? Whatever you do, whatever you try to design, they have to be implemented in reality, and one has to evaluate the performance in reality, right? So if you go to higher frequency scale, the problem that you might face is the facilities. So you might require the resources to fabricate your device, and you might also require resources to validate the performance of your device, right? So these things that one has to look after, right? And then the other important thing is the noise performance. So the communication specialist work with different modulation schemes, which can give better constellation diagrams or better signal to noise ratio or better bit error rate performance, right? So at different levels, people are working at their own capacity, so that they end up giving a solution at higher frequencies, which are meeting the requirements given in the first part, right? So now I work for antenna development. So my focus is on improving the performance of the antennas to establish a reliable communication in the 5G and 6G. But suppose if I am a digital communication engineer, where I am trying to work on different modulation schemes, or I am trying to incorporate more number of factors that one can use to model the channel, or no, it can be anybody else, from the antenna, if it's a transmitter, from the basic signal processing block till the antennas, or if it's a receiver, from the antenna, which is the front end device, till the last part. There are so many people who are involved in. There are RF engineers involved in. No, they will develop the components for such higher frequencies. No, they work at their own level, so that all these people come together to give you a system that is reliable and that is efficient for operation at the 5G and 6G communication standards, right? So my agenda here, as an antenna engineer, I focus only on the development of antennas for such higher frequency ranges. So it's a very popular figure. Everybody must be knowing this. Why we have to go for new schemes at and the new generation. See, if you just imagine the city environment, 2 decades back, and now if you look at the city environment now, there is a hell lot of difference between what was there 20 years back and what was available today. Right? Just imagine, you just go some 3 decades back, right? Instead of 2 decades back, just go to 3 decades or 4 decades back. Communication was not so significant, right? The environment was also not so complex. But today there is a complex environment. There are a lot of environmental clutters that are available that diminishes the received signal at the receiver. Say for example, here there is a base station, and this is your receiver unit, and this green line indicates a direct line of sight path. But no, what arrives at the receiver is the sum of the signals through the direct line of sight path, or from the diffracted path, or from the scatterers, or through the process of reflection. So the envelope is very complex. The received signal will have a very complex envelope, and no, the receiver is efficiently designed so that it can pull out the important information out of the signal. Sometimes based on the clutters available, your signal is prone to more fading, and sometimes your quality of service will be lost. Now, how do I ensure better quality of signal? Right. So that has also been one has to consider. Right. So these are the facts with which people work at their own level and capacity to give you solution at the the 5G and 6G standards. So these are the other techniques that are used for improving the signal to noise ratio at the transmitter or at the receiver site. Instead of receiving signals from one particular antenna, you try to receive from multiple antennas. So there are different types of diversities. If you look at the receiver, there is something called as spatial diversity, polarization diversity, and pattern diversity. When I mean spatial diversity, you just put two antennas, right? And you keep the distance between them at least by one wavelength, and they receive signals, right? Which are from the same base station, but they might have taken different paths. And one might have undergone higher attenuation levels, but the other might not have undergone higher levels as the first signal or the first path would have gone. Right. So what the the processing unit will do is it will receive the signal from both the antennas. It will try to find which antenna is giving good signal to noise ratio, and the receiver will lock onto that antenna and will continue to receive signal from that particular antenna. And suppose if the environment changes, right, because of mobility, the environment changes. Now maybe the first path would be giving you better signal to noise ratio and not the second path. Now what the receiver will do is it will lock on to the first path. It will ignore the signals from the second path, right? And this is called a spatial diversity. And sometimes people transmit information at different time slots, different frequency slots, according to the time diversity and frequency diversity. On the receiver side, you receive the information both in horizontal polarization as well as in the vertical polarization. We call it as polarization diversity. Or you'll have antennas, they create radiation patterns along different directions. So it once again picks energy from different directions, and then you'll make a justification of which is good among the received signal, and then lock onto that receiver. All these are wireless communication perspective, which are rightly integrated onto the system, so that you try to evolve in a system that gives you better signal to noise ratio. Great. So these are some of the processing techniques that are being employed. One is switching, selection, combining, dynamic control. Right. All these are very classical kind of a thing. There's nothing new. All that is new is the concept of deploying multiple antennas for receiving the copies of the same signal. Right. A signal might have undergone reflection, diffraction, or so anything else. So you might be receiving signals from the same signal from different path, right, with the different magnitude, and you collect it, and then you try to find which signal is good, and then you try to establish communication with them. Right. So that's the processing technique. So until this point, we have spoken about some fundamentals of antennas, how the antennas are evolving over time with respect to the generation of communication. Right. Now, I would like to focus on one particular antenna technology. As I told you in the very beginning itself, one of the important component in 6G communications is intelligent reflecting surface. For that, one should have some good understanding of reflect array kind of an antennas, so that the concept can be extended from this generation to the next generation, and therefore one can realize intelligent reflecting surfaces, right? So to make you all understand the benefits of intelligent reflecting surfaces, I must be throwing some light on reflect array antennas that is coming under the high gain antennas now. So we will be talking about what are the existing solutions for achieving higher gain and how these reflect rays are different from the conventional methods. So high gain antennas, as I told you, these are antennas that are required for establishing long distance communication, right? So gain of the antenna can be made higher if the electrical size of the antenna is made higher, right? So larger the antenna's aperture, higher is the realized gain, right? So the classical antennas used parabolic reflectors, as you could see here, right? These are huge dish antennas that were used in the in olden days, or even now people are using these antennas. No, these antennas have this parabolic dish, and these parabolas are characterized by a focal point, and in front of the parabolic dish you see a horn, and all the incident electromagnetic waves are converged at the focal point, and you will try to pick up the high intensity radiation at this point, and then using a cable you just take out all those received signal to your electronic circuit, right? So this is a very classical type of a high gain radiator that was typically used. But no, this antenna is really huge. It's going to occupy a lot of space, right? At the same time, if the target is moving, suppose if you want to communicate with a moving target, right? Like the International Space Station, it keeps moving, right? Suppose if you want to communicate with a moving target, then no, the radiation pattern has to be steered. But these antennas have lack those properties. No, they don't have this beam steering property. So if you want to know position your radiation pattern with respect to the location of the moving target, all that you need to do is you put one bigger size motor beneath the parabolic reflector, and then what you do is you just use the motor configuration to rotate the entire antenna system so that the radiation pattern is also tilted, right? So this is what we call it as mechanical beam steering, right? So huge motors, large parabolic dish, bulkiness makes it less attractive for many of the applications, right? So what happened is people evolved a new method called phased array antennas. Now here what happens is you take a PCB. On the PCB you print a plurality of elements. Now all these elements work together to achieve one single radiation pattern, which is direction. So higher is the directionality, more is the gain, right? Assuming good efficiency, so gain is directly proportional to directivity. So larger is the gain. If the efficiency is so good, the antenna's gain is also very good, right? Now what happens? No, because it is in the printed on a PCB, you can incorporate some electronic components on the surface of the PCB, and then you can alter the bias voltage across each of these electronic components so that you can efficiently steer the beam of the antenna. Right? Say for example, now this pattern is oriented in this direction, right? In this direction. Suppose I want to orient it along this direction. That is still made possible. Still made possible without the use of any mechanical system, but with just the use of what? Some electronic circuitry. Which means that these antennas are little complex when compared to the parabolic dish. But there is always a trade-off, right? The trade-off is that the parabolic dish that you see here, it will work for infinite bandwidth, which means that any frequency falling on the parabolic dish will get converged to the focal point. But unfortunately, these PCBs are printed with antennas which are frequency dependent, which means that you see some elements here, right, printed on the PCB. All these elements are operating at some defined frequency range. Therefore, these antennas are frequency dependent. You cannot use it for a larger frequency range, right? Another limitation with respect to this antenna is that all these antennas have to be connected to a common source point, right? So you will require many transmission lines to be printed on the PCB, and whenever we have transmission lines, the transmission line will suffer from losses, induced losses, right? So that's again a problem. So this is the concept of electronic beam steering. As you can see here, this is the antenna array, and every element in the antenna is fitted with a electronic phase shifter, and the electronic phase shifter is connected to a controller, right? Now, based on your theta requirement, where theta is the orientation of the main beam, right? So, based on the theta requirement, you give weights across these phase shifters, and accordingly, what happens is that the beam gets steered. The constructively interfering patterns are created along certain direction that is defined by theta, right? So, when you want theta to be equal to 10 degrees, accordingly, the weights are altered for 10 degrees. Whenever you want theta for 30 degrees, again the weights of the phase shifters are altered for 30 degrees, right? So that no electronic beam steering happens. So compared to the classical parabolic dish antenna, this antenna is simple to realize and they are much more easy to steer the beam. Now comes the third category of the high gain antenna, which is a spatially fed array antenna. As you can see here, the configuration will typically look like a parabolic dish. So it also has a primary source, that's your illumination source. There is a feed, and in front of the feed, you have a reflecting surface. The reflecting surface is embedded with the reflecting elements. Now, I told you, right, you should be able to compare this antenna with the intelligent reflecting surface of the sixth generation. Now, in case of sixth generation, what happens is that this antenna is a base station, right? This antenna is a base station, and no suppose no there is a receiver here, right? The base station is oriented here, the receiver is here, and no, there is no direct line of sight between the transmitter and the receiver. Now what you can do is you can put an intelligent reflecting surface in front of the transmitter and the receiver, so that the signals that are coming out from the base station or incident on the reflecting surface, they get reflected back, and no, you can also steer the direction of this re-radiation, so that you can collimate all these reflected energy to the other side where your receiver is put in, right? So this configuration you should be able to map with the intelligent reflecting surface of the 6G communications, right? So there is a feed horn, there is a reflecting surface, right? So the configuration looks like a parabolic dish, but there is no parabolic dish. Instead of a parabolic dish, a flat reflector constructed using PCB is deployed, right? So if you look at the bulkiness, this particular antenna system is less bulkier, right? Because it does not use parabolic dish, it uses PCB. The PCBs are embedded with reflecting elements. And because the PCB is used here, there is a possibility of achieving electronic beam steering. There is no requirement for a mechanical beam steering here. You can do electronic beam steering, right? And no, the reflecting surface, if you look here, the number of elements that are deployed on the reflecting surface, right, depends on the gain requirement. Suppose if you want more gain, then there is more participating reflecting elements. If you want lesser gain, then automatically there are only a few number of reflecting elements that will be participating in your overall operation, right? But all the elements that are printed on the PCB, they are not connected together, which means that they work independently, right? So when they work independently, it means that the system do not use a complex feeding network as you had for phased array antennas. The system is not using any complex phase shifting method, and because there is no complex feeding network, there is no transmission line induced losses, right? So in summary, I would say that the spatially fed array antenna combines the best benefits of both reflector array antennas as well as array antennas, right? So to summarize, so this particular table gives me a fair comparison of how the different parameters are related to the classical type of parabolic reflector, the advanced phased array antennas, and the spatially fed array, which I am talking about, right? So as you could see, the bandwidth is infinite for parabolic reflector, but bandwidth is limited for phased array and spatially fed array because they both use elements that operate over a certain range of frequencies, right? Fabrication, you use PCB here, therefore it's simple to fabricate no antennas using PCB. We have established procedures using photolithography, and hence fabrication becomes an easier task. But here that is not the case. Again, there are no feeders used, hence the feeding loss is lesser for parabolic reflector as well as for spatially fed array. However, no, you have transmission line induced losses in phased array antennas, right? So put together whatever I have told you, I have now differentiated them with greens and red, where greens are merits and reds are limitations. Now you can grasp quickly the number of greens that are present across the spatially fed array antennas. So that makes spatially fed array, right? That makes spatially fed array more beneficial, more attractive for long distance point-to-point communication in comparison with the parabolic reflectors and phased array antennas, right? So yes, thus what I'll do is I'll further proceed with the spatially fed array. Right. Again, my intention here is to make you understand the spatially fed array, which can be extended for the development of an intelligent reflecting surface for the 6G communications, right? So when it comes to spatially fed high gain array, there are three different classifications. One is reflect array, second one is transmit array, and the third one is transmit reflect array, right? So all these three are high gain configurations. So if you look at reflect array, from the primary source, the electromagnetic waves are no radiated. So they form no spherical wavefronts. They incident on the PCB that is put in front of it. And if it gets reflected back, as you could see in this picture, the spherical wavefronts are falling on the PCB and it gets reflected back, right? So if it gets reflected back, you get planar wavefront on this side, which is opposite to the direction of radiation from the primary horn, right? So this is the equiphase plane. If you take this plane, all the re-radiated signals will have the same phase value. That's what you call it as equiphase plane, right? Now, if the re-radiation happens in the direction opposite to that of the primary source, then you call this configuration as reflect array. Otherwise, if the re-radiation happens to be in the same direction as that of the primary source, you call it as transmit array. And sometimes you need both reflection mechanism as well as transmission mechanism, making it reconfigurable. And such spatially fed array antennas are called as bidirectional or no transmit reflectors. So reflect arrays are unidirectional, transmit arrays are bidirectional, transmit reflect arrays are bidirectional. It depends on the direction of the re-radiated energy, whether it is in the same direction as that of the source or in the direction opposite to that of the source. So what you see here is the reflect array antennas configuration. It's the real-time scenario. So this is your primary source, right? This is your primary source. This is the reflecting surface. Now what happens? Electromagnetic waves will fall on the parabolic reflector, which is now the flat reflecting surface. And this incident wave is collimated and they're focused onto the horn antenna that is put in front of it. As I told you, antennas are reciprocal. So this entire system, no, they can be configured for a transmitter or for a receiver. If it's a transmitter, energy comes from the horn, falls on the reflector and goes out to the environment. If it is the receiver, it collects the energy from the environment, it falls on the plane, and from the plane, collimation happens and it goes to the primary horn. And then using a cable, you can take it to your electronics. It depends, right? Now, no, instead of a parabolic dish, you have a flat surface. And because it's a flat surface, the collimation, the focusing might not happen, right? Then you have to engineer. Then you have to engineer. What do you have to engineer? You have to engineer the reflecting surface. Then you have to engineer the flat reflecting surface in such a way that the incident waves are collimated to the focal point, right? So as you could see, no, there are some embedded elements on the PCB, but the distribution looks like a ripple. Can you see, no, the circular ripples are getting formed, which means that the reflecting elements on the PCB, they do not take the same size from the center and towards the end. As you could see, at the center, there are large sized elements, and now slowly the size decreases, again increases, decreases, increases, decreases. So the elements that are deployed on the surface of the PCB will take different geometrical values, and these geometrical values are based on some phase difference calculation, right? And you construct the array in such a way that at the end of the day, all these things collimate and produce one single energy that gets picked up at the horn site, right? And no, you can make it beam steerable by deploying the elements with some active devices. When I mean active device, there could be a usage of pin diode or a varactor diode. So varactor can give you continuous tuning, whereas pin will give you tuning from one point to another point. That is discrete tuning, right? So by tuning the phase of these individual elements, you can get an adjustable beam pattern, right? Now again, you just correlate this with the intelligent reflecting surface for 6G. So there is a base station. The base station is throwing energy. The energy falls on the intelligent reflecting surface, and upon incidence, what happens? The beam is steered in a specific direction. Now this direction depends on where your mobile user is, right? Sometimes the user is a stationary access point. Sometimes the user is a mobile entity. Accordingly, either you can create a fixed beam or a steerable beam. So you can create a steerable beam or a fixed beam by properly engineering this meta surface, which we call in 6G as intelligent reflecting surface, right? So I believe I'm making some sense in correlating a reflector antenna with the intelligent reflecting surface, right? So this is the mechanism. So what happens from the horn? The electromagnetic wave is falling on the intelligent reflecting surface or the reflector plane. Now, no, there is a difference in path length between center to center. That is center of the horn to the center of the reflecting surface, right? And the difference is from the center of the horn to the edge. So, no, this is an additional path length, that is towards the edge, the path length increases in comparison with the center to center distance, right? Now, this path difference will give rise to a phase difference, and this phase difference has to be compensated so that you arrive at one single collimated beam along the desired direction, right? Say for example, in this case, the incident waves are reflected in one particular direction, therefore collimation happens in this direction. If you fail to do this, then you get a scattered beam, and no, the net outcome is 0, right? So this is the simple calculation, where this is the difference in the path length, right? And it is multiplied with the propagation constant to get you the phase difference value. Depending upon where the beam has to focus along the elevation plane and azimuth plane, that is theta naught and phi naught, right? You will try to identify the phase compensation required at each and every location in the reflecting plane. So what I'm showing is the side view of the reflector. As you could see in this picture, it's a two-dimensional distribution. Say for example, I create an array of 21 cross 21, right? 21 rows and 21 columns. So at each entry points, at each location of the element, I have to estimate how much is the phase difference. And that phase I have to compensate. If and only if I compensate that phase, I might be getting one collimated beam as shown in this picture. If I fail to do so, then I might be getting some scattered radiation pattern, which will not help me to realize the desired coverage. All right. Okay, this is the transmit array. As you could see, the waves coming from the horn is incident on the reflecting surface, right? Now here reflection doesn't happen. The elements are diverted in the same direction, but what comes out here is a spherical wavefront, but what goes out here is the planar wavefront, right? So these type of antennas are called as transmit array antennas. Now these type of transmit arrays are very much useful in medical applications like treatment of hypothermia, right? No, you can use microwaves for diagnosis. You can use microwaves for treatment purpose as well. So suppose we want to increase the radiation intensity at one particular point, right? Then you can use this kind of transmit array. What it does is it just focuses all the energy into one particular point. Therefore, at that point, what happens is the heating effect happens. Now, what this heating effect will do, it will just destroy the malicious tissue, right? Which can be used for the treatment purposes. So that's what we call it as, no, for medical applications, you can use this transmit array for the treatment of diseases like hypothermia, right? So the lens concept that we study in antennas is applicable here, right? So you can have, a smooth lens or grooved kind of lens. Accordingly, this, Fresnel lens or ordinary lens. No, you can actually have such kind of configurations in your transmit array as well, so that, no, the end game is something that you look for, something that meets your requirement, right? No, as told you, sometimes, no, there is a requirement for the antenna to have both the characteristics, both transmit as well as reflect type of characteristics, right? Just look at the picture. The horn is giving you a directional pattern with a very wide beam width. No, it is not directed towards the red line. The red line is the reflecting plane. And what comes out from the reflecting plane is a highly directional pattern. Right? You just look at the beam width. The beam width is very narrow. Right? Just compare the beam width of the horn with the beam width of this one. No, it's very, very small. So if the beam width is small, automatically the directionality is high. If directionality is high, automatically, no, the gain is large. Right? So if you look at this configuration, if the horn has a typical gain of like 10 dBi, right? If the horn has a gain of 10 dBi, right? Then this configuration can give you gain as high as 20 to 30 dBi, right? So to realize 20 dBi and 30 dBi, what you do is you have to work at the element level so that it gives you what? Larger gain. Sometimes I might require hundreds of elements. Sometimes I might require thousands of elements. Whether I need hundreds of elements or thousands of elements, it depends on the gain requirement, right? So with that, I conclude the fundamentals for the spatially fed arrays. Now we cannot talk about everything, so let me restrict my discussion with respect to reflector array antennas, and then we can just correlate the reflector array antennas with the intelligent reflecting surfaces for 6G communications, right? So these are very popular kind of antennas widely used for radar communications, remote sensing, imaging systems, satellite communications, both civilian purposes as well as defense purposes make use of reflector antennas, and many industries, no, R&D labs are also interested in the development of reflectors. If you look at ISRO, they have this response program. If you write a proposal for reflector array, they will immediately give you the fund for developing the reflector array, because for many years they have been trying to work on the development of a dual polarization reflector array, where for transmission they might require one polarization, for reception they might require another polarization. And now both this polarization has to sit in the same antenna aperture. So one antenna covering both transmission as well as reception, and both may be working at different frequencies, different polarization. That's the biggest challenge that people are finding, right? So ISR has been working for a very long time for the development of such dual polarized transmit receive kind of a reflector. So now just I want you to understand how this reflector is constructed, so that you can immediately map this to the intelligent reflecting surface of 6G communications, right? So if you look at the components of the reflector array, there is a primary source. The feed horn is shown here. It need not be the horn always. It can be any directional radiator, right? It can be any directional radiator, like I can use log periodic antenna, I can use a Vivaldi antenna, right? Even I can use a Yagi antenna. So any low gain or medium gain directional antenna can be used as a source. And in front of the source, what you can do is you can put a reflecting surface, right? So the spherical wavefronts from the primary source will fall on the reflecting surface, and you engineer the reflecting surface in such a way that you give necessary phase compensation to compensate for the path length difference, and therefore you create one directional beam, which is the scattered beam pattern as shown in the picture, and this pattern can be shifted to any direction as per your requirement, because the equation that I showed you has theta value and phi value. So you can fix your theta value and phi value, and you can steer the beam as per your requirement, right? The most critical aspect in the development of the reflector is the design of the reflecting surface, right? As I told you, the source can be anything. So what you have to focus is on the surface. What you have to focus is on the meta surface that is used here, right? This meta surface is the intelligent reflecting surface in 6G, which I am calling it as a reflector, the conventional reflector antennas, right? So suppose if you want to steer this beam to this direction, possible. Suppose if you want to steer this beam to this direction, it is possible, right? Accordingly, what happens? Theta and phi varies, and based on theta and phi value, the phase compensation varies. And what you have to do is you should try to compensate for that phase value. That's it. Now, when it comes to the reflecting elements, the reflecting element can be constructed using conductive materials or dielectric materials. Now, at microwave frequency, people wouldn't prefer to not develop reflectory antennas using dielectric resonators because the resonant frequency of the antenna depends on the height of the dielectric, right? So at microwave frequency, it is typically a bit larger. So what happens is the engineering of such resonators is pretty difficult, and even arrangement, positioning, that is also very complex. Therefore, at the microwave range, people prevent using dielectric resonators. They go for using conductive patches because conductive patches can be easily edged out from the copper cladded PCB, right? Using conventional photolithography process, right? But at millimeter waves, I was telling you about the FR2 frequency range, right? Where you go at a very large frequency at the millimeter wave range. Now, at millimeter wave range, what happens is frequency becomes higher. Because frequency is becoming higher, the height of the dielectric resonator will become smaller. And because this height is so small, you can use the CNC machining to create the desired dielectric resonant distribution on the PCB panel, right? So at low frequencies, conductive patches are attractive in terms of fabrication feasibility. At a high frequencies, like millimeter wave and beyond, people are exploring the opportunities of using dielectric resonators as reflecting elements instead of conductive patches, right? So why should one jump between these two? A comparison is given here in terms of bandwidth, loss, mutual coupling, radiation efficiency, frequency stability, beam tilting. They have their own pros and cons. Now you decide what you want to do, right? Whether you want good bandwidth, go for DR if you're ready to fabricate it. If fabrication is complex, come down to patch. If you want good radiation efficiency, you can go for DR, right? Conductors are prone to thermal losses, but dielectric resonators, they are not prone to thermal losses. What they have is only dielectric induced losses, and you can minimize these dielectric losses by choosing low loss materials, right? And again, because they are
Speaker,
made
speaker
dielectric material, the coupling is lesser, right? So you know that the mutual coupling severely affects the radiation properties of the antenna, right? So such coupling effects are not available in dielectric resonators, or they are kept at a very small level when compared to the counterpart, right? So based on some of the important attractive features of your own design, you can choose to develop your reflector array either using conductive material or using dielectric resonators, right? And now the design procedure. As I told you, the most critical aspect in the development of the reflector array is the design of the reflecting surface itself, which is nothing but the combination of a PCB and a reflecting element, that is the radiating element, right? There are a few important parameters that you have to focus on. One is the reflecting phase, the other is the reflection efficiency, third one is the beam width of the element, and fourth one is the bandwidth, right? See, whatever comes from the horn, they should get reflected back. 100% reflection you look for. If and only if you reflect everything, it's a good reflector. If you reflect only 50% of the energy, and if you dissipate remaining 50%, that's a poor reflector, right? So the choice of reflecting surface will dictate the overall efficiency of the antenna itself. So if you are trying to develop an intelligent reflecting surface for 6G, this intelligent reflecting surface should have good reflection efficiency so that the base station can communicate with the mobile user or a stationary user under all cases of the obstacle that is present between the users and the base station, right? So these are the steps involved. The first thing, the specification for what frequency you have to do. What is the theta value and phi value you want to extend the coverage? How much gain you are looking for? Based on that, you can choose the radiating elements that will meet your specification. And then step number 3, 4, 5 is very, very important. Step number 3 is, I said it's a 2D plane. So in the 2D plane, at each and every point, you have to look at how much is the phase compensation required. So you will compute that using some software codes, and you have to identify a suitable geometrical parameter that will compensate this phase error or phase difference, right? So at the first level, you will find at what location what is the phase compensation required. At the second level, you will try to find for what geometrical variation, how much phase compensation you will realize. Now, in the first case, it's location versus phase, and in the second case, it is phase versus geometrical parameter. Now, in both these cases, what is common is phase. Therefore, now you can relate the location to the geometrical information. I repeat, in the first case, you try to find at what location, how much is the phase required, location versus phase. In the second case, you will try to find for this much amount of phase difference, how much should be the geometrical parameter variation. In both these, phase is a common parameter. By using these two, you can map for the given location what should be the geometrical parameter. By this way, you can construct the reflector array and do a small level of optimization, right? So these are some of the typical traditional radiating elements. So these are the aperture coupled radiating element, right? So with single polarization, with dual polarization. Now again, these are dual band reflecting elements. The reflecting elements are constructed using square loops. They have used cross dipoles and square patches for realizing dual band reflecting surface. It's a single layer design. These two are single layer design. Whereas this is a dual layer design. On the top layer, they have a cross dipole. On the bottom layer, they have a square patch. Right? Now, as you could see here, this is the this has higher, larger dimension. So this corresponds to low frequency, and this is smaller dimension. It corresponds to high frequency. One low frequency element can accommodate 4 high frequency elements. Right? Now, what happens if you look at the two elements, two neighboring elements? These two elements will see different phase difference because of the location. Therefore, the phase compensation required at this element is different. The phase compensation required at this element is different. That's why you see here the phase compensation is achieved through the delay lines. This has got a longer length and this has a shorter length, right? And within this cell, you see there are 4 high frequency elements, right? They all have the same geometry, but if you look at the phase compensating length, it's different because the phase difference at high frequency at this location is different, at this location is different, at this location is different, and at this location is different. So for each and every location, you will try to identify how much is the phase compensation required, and accordingly, you will provision the phase values, right? Phase compensation values. Now I told you 2 things: 1, location versus phase, and 2, phase versus geometrical parameter. The geometrical parameter here is the delay line, and what is getting varied is the length of the delay line. So for what phase variation, right? What should be the geometrical length variation, and where it has to be deployed? That is clearly studied. As you can see here, these cross dipoles are having larger dimension compared to square patch. So there are 4 cross dipoles operating at low frequency, and each low frequency dipole can accommodate 4 high frequency square patches. Now just look at the size. The 4 cross dipoles are having different sizes. The 16 square patches are having different sizes. Right? Why do they take different sizes? Because they encounter different phase values. Right? And if you look at this case, one cross dipole can accommodate 16 square patches, where cross dipole can accommodate can work for X-band frequencies, and square patches can work for K-band frequencies. Now again, look at the size of the square patch. They might not be the same, right? Why they are not same? Because they are receiving signals for different path length. Therefore, there is phase difference, and they have to be compensated. And how they are compensated? By adjusting the geometrical parameter. So the electromagnetic wave that is getting incident on this surface, right? They get reflected along a particular direction with same phase. so that they collimate and create maximum energy along one desired direction. Right? So these are other radiating elements like the rings. Right? Now here what happens is they have changed the orientation of the splits. Right? So the variation in the splits can be used for adjusting the phase compensation. Right? Again, dipoles are used, low frequency dipoles and high frequency dipoles. And there are two different splits, right? So one for the X band, the other for K band, making it a dual layer. So all these are some of the techniques that are used. No, in the earlier slide, I showed you that there is certain distribution of elements in the reflecting plane, as you could see here, right? There is a circular distribution, right? Now, this distribution is very much symmetrical. If I just make it, divide this into 4 quadrants, you can see the mirror image along the 4 quadrants. So, this kind of distribution will give you single radiation pattern, right? Suppose if you look for multiple radiation patterns, multi-beam, right? Then accordingly, you will compute the phase value and you will arrive at the distribution. As you see in this case, so what happens is you could not see that circular distribution. The reason is that the engineering is done in such a way that it creates multiple radiation patterns, right, from the incident electromagnetic wave. So suppose now let's assume at 6G frequency, this is the intelligent reflecting surface. There are multiple users surrounding this region. Now this is the base station. So what can happen is the electromagnetic wave from this base station can incident on the intelligent reflecting surface, and now they radiate it in 5 or 6 directions depending upon the requirement, and all 5-6 directions will point to some user along that particular direction. Right? So this is how it is done. Now this is one simple example that helps you to understand how the geometrical variations will help you achieve different phase values. Now I'm running out of time, so what I will do is I will quickly get into one of my research topic. Right, so I'll just get into the this is the multi-beam radiation pattern which we were talking about, right? So now you can engineer the reflecting surface in such a way that it can create multiple patterns along different directions. So if the intelligent reflecting surface necessitates to serve 4 users, then 1 user along this direction, 1 user along this direction, 1 user along this direction, and 1 user along this direction could be put on, right? Now this can be the meta surface. This can be the element that can be used for constructing the meta surface, right? So accordingly, what we have done is we have developed electronically reconfigurable reflector array. So it's called a compound reconfigurable reflector array antenna, right? So it's called compound because it can work in multiple frequencies. It can also provide beam steering along multiple directions, right? So this is what. So what we presently have is that either the frequency is fixed or the radiation pattern is fixed. When you try to change both, when you try to work in different frequency bands and you also simultaneously try to achieve beam steering, then it becomes a compound reconfigurable reflector array, right? So otherwise we can call it as a smart reflector array, which is one of the important requirement for next generation communications to serve the users better, right? So these are some of the objectives of our research. We try to develop a reflector antenna that can work in the X-band frequencies. It can also simultaneously work in the uplink and downlink frequencies in the Ku band, right? So for this, now what we have done is for switching frequencies, we use pin diodes, and to steer the beam, we use varactor diodes because varactor can give you continuous beam steering, right? So this is the design procedure. As I told you, the most critical aspect is the development of the unit cell. And after the development of the unit cell, first we focus on frequency reconfiguration by integrating pin diodes. And then we focus on beam forming by integrating varactor diodes. And then we do a large scale optimization to get the desired output. So as I told you, we use pin diode for frequency reconfiguration. So when the pin is in the off state, it works at Ku band uplink, and when the pin is in the on state, it works at Ku band downlink and the X band frequencies. And for phase compensation at 14.5 GHz Ku band, we use varying path size, and for Ku band downlink and X band, we have used varying delay line. Okay, and then for beam steering, we have used varactor. So this is the unit cell that we have developed. So there is a square loop, and within the square loop, we have a volta cross. As you could see, above and below, there is a pin diode and varactor diode. When the pin is in the off state, only this particular unit cell will work for the desired KU band. When the pin is in the on state, it works for other KU band and in the expand frequency scale. This is the architecture diagram. So we have used two substrate. One substrate to hold the biasing circuit, another substrate to hold the reflecting elements. Right. So we have used a simulation tool called CST Micro Studio Shoot to characterize our unit cell. Right. So again, so when the pin is in the off state, now what happens to the reflection phase and the reflection magnitude that has been studied, right? And for the other case, this is for one frequency, that is pin is in the on state, off state. When the pin is in the on state, it has to work for the other band, that is the downlink and X band. But for downlink and expand, it might require a different phase value. But what is existing because of the square patch variation, it's a different value. So I can estimate how much is the error that is present. Now that error can be compensated using a delay line matrix, right? As you could see in this picture, when the pin is in the off state, this line is disconnected. When the pin is in the on state, it works at the downlink frequency X band. During that time, there is a difference in the error that is getting compensated by the use of what? This varying delay line length. Right? So accordingly, this is the delay line matrix. So at each and every cell site, how much should be the length of the line that we will calculate? So these are the specifications of the electronic components that we have used for our design. SMP series and SMV series are used, right? And we also used a proper filtering structures to effectively isolate the RF component and the DC components. So this is the reflector that we have developed. It's a compound reflector array. Yellow is taconic. The other one, the cyan color is the Rogers. So this is the front view. This is the rear view, right? So these are the biasing lines. And for electronic beam steering, we again studied what should be the bias voltage across each and every varactor. For different tilt angles, we estimate how much is the biasing required across each and every varactor diode. This is the overall working diagram. So now what we do is we have used the PC-based control system where an Arduino-based solution is used, right? So we have DAC modules that will convert digital to analog signals, and these DAC modules no output. It is connected to the electronic components for biasing the pin diodes and the varactor diodes. So more details is shown here. So as you could see, this is the Arduino board. So serial to parallel converter. We have used 3 DAC modules from Texas. Now each has got 96 channels. It is then given to a 300 pin FMC connector. Now each connector, each pin will be connected to a particular bias line in the reflector. So based on the information, that is the tilt value, based on the tilt value, based on the frequency to be operated, the lines across each FMC pin will bias the pin diode and the varactor diode. So this is a board diagram. So as you could see, there are 3 DAC modules available, right? So this is the testing phase where we just tested how much is the voltage present across each and every pin across in the FMC connector. This is a fabricated prototype, right? So this is your primary source. This is the reflecting plane, and this is a DAC module. So we have used press type module. So we have initially did for a static functionality, which means that this particular module is programmed for one particular frequency and one particular tilt angle. Accordingly, the bias values are exciting each and every component on the surface of the reflector plane. These are the estimated radiation patterns of the proposed array. As you could see, it works for both uplink, downlink, and X-band frequencies as expected. And these are the beam steered radiation patterns. We have tested for 2 different angles, plus or minus 10 degree and plus or minus 20 degree. And that's what. So we have developed a frequency reconfigurable beam steering reflector antenna using a simple electronic control board, right? So with that, I conclude my presentation today. We are almost about to end. Apart from that, we also work on several other important topics related to antennas and propagation. So thank you so much for listening. And if you have any queries, I'm open to discuss. Thank you.
Thank you, sir. Participants, if you have any queries, you can unmute yourself and ask. Participants, if you have any queries, you can unmute yourself and ask. Okay, in the meantime, I request you all to turn on your video for a photo session. Participants, please turn on your video for the photo session. Jasmine, ma'am.
Yes, ma'am. Yes, I'm taking.
Are you done with it, ma'am?
Yes, 1 minute.
Okay.
Yeah. Yes, ma'am.
Okay. Thank you. Participants, if you have any queries, please unmute yourself and you can ask. So I hope there is no queries. So Jasmine, ma'am, shall we end the session?
Yes, ma'am. Yes, ma'am.
Okay. So on behalf of our institution, organizing committee, and all the participants, I extend my heartfelt gratitude to you, sir, for delivering such an insightful session on the role of antenna in next generation communication. Your expertise and clear explanations, both on theoretical concepts and practical applications, have truly broadened our perspectives. We are confident that the knowledge you have shared today will greatly be beneficial for our faculties and even the researchers. Thank you once again for your valuable time, effort, and commitment to make this FDP a memorable and enriching experience. Thank you so much, sir.
Thank you so much, organizers. I wish you all a very great success, and I wish the organizers for the successful conduct of this FDP. Special thanks to Jasmine ma'am for inviting me here. Thank you all. Best wishes.
Thank you
Thank
for
you.
your kind wishes, sir. Thank you so much.
Thank you, sir.
Uh, Jasmine, ma'am,
Yes, ma'am. You
so shall we connect back after 15 minutes?
after 10 minutes, ma'am.
10
So
minutes. Okay. So participants, you can have a break for about 10 minutes and please join us back by 7:40. The time is right now 7:30. You can join us back by 7:40.
kindly join by 7:40 because the speaker will be
Already.
joining in. Is already she's ready. So please don't delay. Join by 7:40 without fail.
Okay, ma'am.
Okay, ma'am.
கண்டிப்பா கொஞ்சம் தங்கச்சி உங்க மேல காட்டுற அன்புக்காகவும் நீங்க வந்துதான் ஆகணும்
இல்லையே இப்ப அவங்க பேசுறாங்களே, அவங்க வந்துட்டு இருக்காங்க இந்த கடைக்காரங்க. கொரியர் கடையா?
என் பேர்
தம்பி
Good evening, ma'am.
Good evening, ma'am.
Good evening, ma'am.
Good evening.
Jasmine, ma'am.
Yes, ma'am. Mangai, ma'am.
Let's
You
start,
can
ma'am.
start. Yes, ma'am. Yes, ma'am.
Okay. Good evening to all. Next session is on edge and fog. Audible. Good evening to
Yeah,
all. Next session is on edge and fog computing for real-time industrial applications. Now I call upon Dr. S. Hemalata ma'am, Assistant Professor, ECE Department, for giving introduction about the speaker, Dr. S. Benila ma'am.
Yes, ma'am. Good evening, everyone. It gives me immense pleasure to give an introduction about Dr. S. Benila. Dr. S. Benila is a senior grade assistant professor in the School of Computer Science and Engineering at Vedur Institute of Technology, VIT, Chennai. She brings over 15 years of academic experience, having previously served at SRM Valiamma Engineering College from 2008 to 2023. She holds a BTech in Information Technology from St. Xavier's Catholic College of Engineering 2006 and an ME in Network Engineering from Arulmigu Kalasalingam College of Engineering 2008. In 2022, she earned her PhD in Information and Communication Engineering from Anna University. Dr. Benila's research interests include computer networks, network security, edge and fog computing, data analytics, and artificial intelligence. She has published over 15 research papers in Scopus Indust and SCI journals and has presented her work at numerous international conferences. In addition, she holds 4 patents in her areas of expertise. She is an active member of several professional organizations, including Indian Society for Technical Education, ISTE, Computer Society of India, CSI, Indian Science Congress, Society of Digital Information and Wireless Communications, STIWC. Dr. Benila also contributes to the academic community as a reviewer for Springer Nature journals. So to know more about edge and fog computing for real-time industrial applications, we would like to call Dr. S. Benila to share knowledge on edge and fog computing. Please to start the session, ma'am.
yeah. Thank you for the introduction, ma'am.
Start the session, ma'am.
Yeah, yes, ma'am. Is the screen visible, ma'am?
Ma'am, it's not visible, ma'am.
No,
Just a
ma'am.
minute.
Yes, ma'am. It's now it's visible.
Okay, okay, ma'am.
Thank you.
Good evening, everyone. Welcome to this session on edge and fog computing for real-time industrial applications. I'm Dr. Benila from Vellore Institute of Technology, Chennai. Today, we will explore how edge and fog technologies are reshaping modern industry, especially in mission critical and real-time context. So at the end of this talk, we all can know what is this fog and edge computing paradigm, how it influences the industry 4.0 standards, and so on. So this is the roadmap of our presentation. First, we will start with the definitions and concepts of edge and fog computing. Then we will dive into industrial real-time requirements that are demands of mission-critical industrial application, and then the architectural and frameworks that are used for real-world use cases, real-world applications, and the use cases in Industry 4.0. After that, the research challenges in fog and edge computing and the tools and platforms that are used for implementing this real-time applications using fog and cloud, fog and edge. After that, the future directions of this technology we are going to cover. So the evaluation of computer paradigm, at the beginning, it started with the centralized mainframe computers. So the centralized computers are powerful but limited in reach. Then the cloud client server models and distributed access came into play. Here, all the decisions are taken by the server systems, and then it is moved towards the edge cloud computing. So here we gain the scalability and on-demand resources, but cloud alone can't always handle real-time industrial needs. Now we are moving towards the edge and fog computing. Here, the processing is closer to where the data is generated, and we are even moving towards real-time AI at the edge. So this shift is not about computing. So here it plays a major role where the data is generated. At that place itself, the analytics and processing is happening. So why we are moving towards this fog and edge computing means, so in real time and mission critical application, the latency plays an important role. So for this latency requirements and bandwidth cost and privacy issues, all pushing us towards the decentralized computing. So the paradigm, this edge and fog computing, it is a paradigm shift from compute in one place to compute everywhere it matters.
Evaluation of computing.
So what is the driving force? What is the key drives for distributed computing in industry? Why do industries really need distributed computing? First, the explosion of data. The billions of endpoints make central processing impractical. Most of the sensors and other devices, it generates billions of data at a particular time. So if we are transferring all the data towards the cloud for processing, it creates delay as well as bandwidth. All the bandwidth can be used only for sending the raw data over the network. Second, safety critical systems like industrial robot need immediate responses. So delays cannot be tolerable in this type of industrial application. When the network cost and bandwidth make it impossible to send all raw data to the cloud. So we are moving the data analytics near to the data where it is produced. So that's the main purpose of moving towards this fog and cloud computing paradigm. Then why Industry 4.0 need this cloud and fog computing? So if you are considering the Industry 4.0, here all the processing are automatically done. So if we are considering the cipher physical systems, here the delay, it should be in sub-millisecond. So if we are transferring all the sensor data to the cloud for processing, the round trip time for sending the data and receiving the response itself is taking too much time. So it is not tolerable in cyber physical system. Similarly, the autonomous coordination in AGVs and robots, the maximum expected delay, tolerable delay is 5 to 50 milliseconds. Then inline defect detection and quality control, the maximum tolerable delay is 200 milliseconds. Then digital twins with low latency update, the maximum tolerable delay is 500 milliseconds. But if you are transferring all the data towards the cloud, it takes about seconds to process the data. So in this type of mission critical applications, the usage of cloud only is not possible. So we are moving towards the industry 4.0. It uses cloud and edge and fog computing for processing its data. Then next, why cloud alone is not sufficient for real-time industrial applications. While cloud offers immense scalability and huge data processing servers and processing capability, but it is lacking in terms of latency, bandwidth, privacy compliance, and reliability. So if the physical distance between the sensors and the cloud is very high, so it produces more network delay. So it introduces unpredictable delays when the raw data is transferred towards the cloud, and then the analytics are done in the cloud. After that, we are receiving the response back. So it creates unpredictable delays. So it's not sufficient to use the cloud computing alone for this kind of application. Then the bandwidth requirement. So if the sensors, for example, if you are having a CCTV surveillance camera inside an industrial building, there are more number of cameras are there. So it is producing huge amount of data at a particular time. So if you are transferring all the raw data towards the cloud, the entire bandwidth can be used only for sending the raw data. So the volume of data is high. So the entire bandwidth is used only for sending the raw data itself. Then privacy complaints. So for example, if we are transferring all the raw data towards the cloud, it takes the public network to send the data itself. So if we are transferring the raw data directly to the cloud servers, then the sensitive data may be stolen and it can be hacked by the hackers. Then reliability. So here industrial operations cannot tolerate disturbances. So we are using the cloud and fog computing for processing this kind of data. Then why we need this fog and cloud computing? The first thing is, so critical latency demands. The second one is impact on critical system. So high latency, jitter and packet loss can lead to operational failure. For example, the robotic arms are used in the automation system. Can you please mute your Selvi ma'am? So high latency, jitter and packet loss can lead to operational failure or hazardous condition in mission critical application. Then this the optimal solution for this thing is we have to use edge and fog computing for processing the industrial real-time challenges by bringing computation closer to the data source. So we are integrating this edge, fog and cloud computing together to process the real-time data which is being produced by a large volume of sensors. So here we are processing data near to the data source, that is considered as edge computing. Then if you are considering about fog computing, it is an intermediate layer that is in between the edge and the cloud. So edge computing, the computing capabilities are available closer to the data where it is produced. Cloud, it is far away from our data source. Then fog, it is an intermediate layer. It lies in between the edge computing layer and the cloud layer. So here, edge computing, so it brings computational power and data storage as close as possible to the data source. So wherever the IoT devices are placed, in that place itself, the computation has taken place. The computing capabilities are extended and that are available at the data source itself. That is considered as edge computing. So here processing at or near the data source. So it minimizes the data transfer distances. Normally the gateways, embedded servers and routers are placed near to the data source. So the main advantage of using this edge computing is it reduces the delay because the data processing is happening at the network edge itself. Then the fog computing. So fog is it is similar to the cloud, but it extends the features of cloud towards the edge. So normally in edge computing or edge layer, we can't place lot and lot of processing servers there. So if we are placing everywhere at the edge, then it becomes like a standalone network or standalone processing. But if we are using fog computing in between the edge layer and the cloud layer, it extends the features and capabilities of cloud server towards the edge. So it acts as an intermediate layer in between the cloud and the edge devices. So it is a distributed architecture. Here we can process the data closer to the network edge. So fog is similar to a cloud. It extends the features and capabilities of cloud towards the edge devices. Then if we are transferring all the data directly to the cloud, the raw data are overwhelming and it affects the network bandwidth and everything. So all these aggregation is done or local processing is done at the fog server. Only the insights are forwarded to the cloud. So instead of sending all the data directly towards the cloud, first we are processing the data inside the fog servers. Fog servers provides local analytics, it provides the insights, it provides decisions, and then for global decision making, it transfers the insights only to the cloud server. It will not transfer all the real data directly to the cloud server. It processes it locally and it transfer the insights or the results only to the cloud server. So this is the fog computing architecture. Here we have IoT devices at the local premises. After that, we are having the fog nodes. So fog nodes, it extends the features of cloud servers. Then it provides local analytics, aggregation, and then it transfers the data towards the cloud for global decision making only. So it's not transferring all the raw data to the to the cloud servers. It processes it locally, and for creating global decisions or global decision making or historical analysis, for that purpose only, it forwards the data towards the cloud server. Then this is the distinction between fog and edge. So the first one is the edge computing, and second is the fog computing. So edge computing, the computing is performed near to the device, and the fog computing, it is in between the device and the cloud. Then scope is local. Here in fog, regional or distributed data processing is happening. So if you are considering about the latency, in edge computing, it is ultra low because the processing is available at the edge itself. Then for computing, it is very low. Then data volume, here it process the small data streams or raw data streams are processed. In fog servers, it aggregate and filter the data. Then computational power, so fog resources are resource constraints because we cannot have all the servers and processing units inside the factory or inside the cities and anything. So it is limited, but fog, it can extend the features from the cloud. So moderate server grade nodes are there. Then these are the examples. Smart sensor gateway for real-time anomaly detection. So if you are detecting the defective parts in the manufacturing industry, at the time itself, if you are including the local processing there, it will alarm. It will create one alarm whenever there is a defect is going to happen. And before finding out the defect itself, it shows the defective parts. But here, industrial controller and cluster management comes under the fog computing. Then real-time requirements in industry. Why we are going for this fog and edge computing? So because of latency constraint, mission critical reliability, safety compliance, and offline operations. So then Industry 4.0 and edge fog computing, these are the scenarios, the use cases where we are using this cloud and fog computing. For cyber physical system, for processing real-time data at the edge, it enables seamless integration of physical and cyber components. Then smart factories, local intelligence, optimizes production line, quality control and resource management. Then predictive maintenance, so on-device analytics to detect anomalies and predict equipment failure before downtime. Then digital twins, edge devices feed real-time operational data to virtual models for continuous optimization. Then if we are integrating edge, fog, and cloud architectures in action, what is happening? Here we can combine all the things together. So first, the data is produced and we have number of edge devices. So edge devices perform local processing, and then the fog layer. So fog layer provides intermediate and local analytics. Then the cloud layer, the processed data from the fog layer is given to the cloud layer for global decision making. So the cloud layer has most of the data analytics capabilities. Large, huge volumes of data can be handled, and it can collect historical data from different servers. So all these things can be combined together, and it can provide the global insights regarding to our applications. Then the key advantages of combining these technologies. First one, reliability and fault tolerance. So first, it has redundant lines. Instead, if there is a single node failure or single line failure, it can be handled by the redundant lines. Then local decision making. If you are including the fog node, it can process the data and make autonomous decision without relying on continuous cloud connectivity. So local decisions can be made by this fog servers. Then self-healing network. So this fog nodes and edge nodes are designed with intrinsic self-organizing and auto-recovery mechanism. So they can detect failure, reroute traffic, and recognize themselves to maintain the service availability. Then the second one is optimizing resource management. So if we have fog servers in between the cloud and edge, then if in the fog servers, it has more number of servers inside. So if one server is experiencing very high load, it can be transferred to other node. That is called load balancing. So instead of taking all the processing in one server, if the server is busy or the server is handling too many requests, at that time, dynamically distribute the workload to the adjacent or the next fog resources, fog servers. The next one is task offloading. So task offloading means if the fog server is not able to process the data, then the data is forwarded or the data is sent to the cloud servers for further processing. Then energy efficient scheduling. So here in fog server, the load balancing, task offloading, and energy efficient scheduling are the three main tasks that can be performed in a fog server. If the fog server is having limited resources or it can't able to process all the data at that particular time, it transfers some of the workload to the nearest fog devices or fog servers. That is called load balancing. Even it cannot distribute and process the data with the help of other fog servers. It transfers the workload to the cloud server. That is called task offloading. Then energy efficient scheduling. So to minimize the power consumption, it uses different scheduling techniques to process the data and offload the data to cloud servers or other fog servers. Then the use cases where we are using this cloud, fog, and edge integration. Here the first use case is smart grid application. So in smart grid application, we have smart meters in. So if we are deploying the smart grid, then smart meters are deployed in each and every homes and business units. So the edge devices, the smart meters collect the real-time consumption data, and then the substations are acting as fog node. So the local substations aggregate this data from the meters and manage energy distribution within a specific district, or regional updates are happening, or aggregations are happening in the fog node. After that, the cloud provides the centralized processing. So for long time forecasting and grid-wide load balancing, the cloud servers came into play. So the edge devices, the smart meters are acting as edge devices. It collects the data and it sends the data to the fog nodes. The fog nodes, the substations are acting as fog nodes. So it contains the processing servers in it. So it aggregates the data from the meters, manage energy distribution within the specific area, and then it balances the load. After that, it sends the processed data to the cloud for creating the long-term forecasting or grid-wide load balancing and energy trading decisions. Then the next application is autonomous vehicles. Here, the autonomous vehicles have a lot of sensors in it. So the powerful edge processors, it enable real-time perception, path planning, and immediate decision making for safe navigation. And the roadside units, if we are implementing the smart transportation system, so each vehicle has a lot of sensors and small kind of processors in it. So if the vehicle is going to collide with some other vehicle in the close proximity, then the edge processors can process it, guide the vehicle for safe navigation. And then the information about the road conditions and the traffic and everything is given to the roadside units. So the roadside units collects the data from different vehicles, and it takes vehicle to vehicle communication, vehicle to infrastructure communication, regulate the traffic flow in one particular area. So all these things can be handled by this fog servers or the roadside units. Then fleet management and update. If you want to provide a global warning about the traffic management in a city, particular city, then the all roadside units send their insights about the particular traffic in that particular area to the cloud servers. So the cloud server collects all the data from the fog servers and it makes aggregate decision, and then it provides some machine learning and AI models, and it runs the different types of algorithm and predicts the overall traffic in the city. Another one is healthcare IoT. So wearable devices. The patient is having wearing the devices and it collects the data. And the hospital gateway is considered as a fog node. So all the data collected from the patient are transferred to this fog nodes, and it will create immediate alerts to the care team about the health condition of that particular patient. Then if you want to create the data and insights about the studies from different hospitals, the connected network is there, means uh, fog nodes from each hospital send the decision to the cloud server. Then cloud server, it gets the data from different servers and process it and provide the global healthcare decision about the particular patient or particular hospital. Then smart manufacturing. Here we have edge automation. After that, the local analytics is happening. Then for coordination, and finally, for creating the final decision, the data are sent to the cloud for processing. Another one application is smart agriculture. Here in the paddy field, we have different sensors. The sensors collect the data about the information about soil moisture, nutrient levels, pH, and crop health. Then this data, raw data, is given to farm hubs. So we have localized fog nodes there. It collects the data from hundreds of sensors and it provides real-time analytics, recommend precise irrigation schedule, pest control mechanisms, and optical harvesting time. After that, if we want to create a global decision, the data is transmitted to the cloud. So the cloud integrate the weather forecasting, historical yield data, satellite imagery. It combines everything together and it provides a large-scale predictive modeling for crop yield, disease outbreak, and market trends. Then industrial use case, here in smart factory, the cloud, fog, and edge integration can be used. So edge devices collects the data about the machinery, products line, robotic arms, and operational data. It is given to the edge servers for immediate processing. After that, the fog servers collect and provide the coordinator process, optimize the workload, and give some local analytics. After that, for providing the global decision, it is given to the cloud servers. Then this is mining industry. So in the mines, we have environmental sensors. It monitors the air quality, gas level, and structural integrity. Then on-site control centers are there. This information, the environmental sensors collects the data and transfer the raw data to the on-site control centers. After that, it takes immediate responses to hazardous condition and operational adjustment, aggregate data for regulatory compliance, long-term geological analysis, and predictive maintenance are carried out by the cloud server. So for implementing this fog and edge, we have lot of tools and platforms. So the first one is Edge X. So Edge X Foundry, it is an open source vendor neutral IoT edge platform. So by using this, we can create our own fog and cloud applications. Then the second one is Open Fog Reference Architecture. So it provides the framework for creating open fog for building secure, scalable, and resilient fog and fog computing environments. Then Azure IoT Edge, Microsoft managed service that extend cloud intelligence and analytics to edge devices. Then AWS Green Gas. So this is provided by Amazon Software that extend AWS cloud capabilities to edge devices, allowing local execution of AWS functions and secure communication. Then the benchmarking and simulation tool, if we are creating our own IoT based edge and fog computing application, we can use any one of the simulation software. Usually this iFog Sim, this is a popular simulation toolkit for modeling and evaluating the performance of fog computing devices. So for usually for research purposes, all this fog kind of implementations were simulated by using this iFog simulation. And Edge Cloud Sim, so this is the extension of Cloud Sim, specifically designed for simulating heterogeneous edge computing environments. So if you are considering about the edge computing only, then we can go for Edge Cloud Sim. If we are implementing or simulating the fog features, then we have to go with this iFog Sim. Then Omnet++, this is discrete event simulation environment for modeling communication network, including fog and edge topologies. So all these are open source simulation tools only. We can use this for our academic research and other kind of purposes. Then advances in edge and fog computing and industrial IoT. So this is one example how edge AI model is deployed. Here we are demonstrating the real-time vibration anomaly detection in industrial motors. So here the TensorFlow or PyTorch can be used. So how it can be implemented by using iFog SIM. So first we have to create the required components. So the components for this integration is edge devices, fog nodes, and cloud. So here we are considering the vibration sensors as edge devices. So this edge nodes run lightweight AI model. Then fog nodes aggregate data from multiple edge devices, run pre-processing and intermediate analytics. After that, cloud. So it train and update AI model, perform historical analysis. So first, the required edge nodes, fog nodes, and cloud nodes has to be placed. So for creating the devices by using iFog SIM, this is the code for creating the devices. How many devices we need? We can create that much devices. After that, we are creating sensors and actuators. Then define the application with Edge AI module. So what processing the edge device need, it has to be implemented by using this Edge AI module. After that, we are placing the edge AI deployment. Then we are running the simulation. This setup was given with edge computing only. We are not including the fog setup here. So far, till now, we have seen about how this edge computing and fog computing provides local analytics and how it can be applied in mission critical applications. So if the application is intolerant to delay and network bandwidth limitations, for processing that kind of data, we are going with this edge computing or fog computing. So if we don't need the local processing and global analytics, then we can move towards edge analytics. But if we need a global outcome or global result from all these kind of sensors and local processing, then we have to go with fog computing. Then even we are using different kind of computing, for example, fog and cloud. If the communication speed and the network speed is low, we can't uh, we can't get the required outputs. So the integration of 5G is also important in this context. So the convergence of 5G, AI, and Industry 4.0 comes to play. So 5G's pivotal role in fog and edge computing. 5G, it has ultra low latency, high bandwidth, and massive device connectivity. We can connect millions of IoT devices per square kilometers, and the data transfer speed is very high. And then ultra low frequency, the response time is less than 1 milliseconds. Then it can be combined with this 5G network can be combined with edge and fog computing, allowing data processing to occur closer to the data source. For example, a self-driving car need both edge computing for local decision making and 5G for fast communication with nearby vehicle. For example, if we are implementing autonomous vehicle setup, so at that time we need both of these things, edge computing for local decision making. If the car is moving in a wrong side or it is going to collide with some other vehicle, then the local decision has to be taken place at that particular moment. Then if we want to communicate with other vehicle or roadside vehicle or the transport department, then we need 5G communication for fast data transfer. So this the integration of 5G and edge, it produces fast and reliable communication, local processing power. So here one example case study is given in a smart city surveillance. So see, the CCTV cameras are deployed everywhere. So it produced enormous volume of data. So the 5G send this data and summarizes it and produce critical alerts to the cloud for deeper analysis. So if we need local processing only, we can directly go with edge computing, but we need deeper analysis and global decision making, we have to go for the cloud computing paradigm. Then the intelligence layer, AI in edge and fog. So now everywhere the AI technology has been introduced. So we can integrate this fog, cloud, and AI for processing the time critical applications. Then one more important thing in edge and fog computing is federated learning. So all the recent research it focus on federated learning. So federated learning means instead of sending all the raw data to the server for processing, first we are processing the data. So the local training is happening at each and every places wherever the IoT edge devices are deployed. So, for example, in a factory setup or healthcare devices, here the example is given with healthcare devices. So, wearable devices can produce large and large amount of data. So, the smart hair wearable train AI models on individual patient health data locally. Then, instead of sending the patient's raw data directly to the fog server or cloud server, the local training is done at the edge premises itself. After that, it gets the trained model and then it shares the trained model only to other fog devices or cloud devices. Instead of sending the raw data, the local analytics happen place at the data source itself. So local training is happening and it gets some local processing and it gets some decisions. After that, the decision only is shared with other fog servers or central servers. It does not share the raw data. So it preserves the privacy of that particular patient itself. Instead of sending the raw data about the particular patient, it takes a local training and local decision is happening and the end results only are shared with other devices and central server. Then transforming industries with the edge and fog. So here, smart manufacturing, advanced robotics and automation, and healthcare, smart mobility. All these applications are using edge and fog with 5G communication. So why we are using 5G in edge and fog computing means 5G is faster when compared with other communication technologies. Then if we are integrating AI, then it supports real-time decision making, reducing cloud dependency and improving responsiveness. And federated learning, if we are using federated learning, it enhances data privacy and reduces bandwidth by sharing only model updates, not raw data. Then Industry 4.0 transformation. So the edge for computing for smart manufacturing, automation, and advanced analytics. Then this fog and edge computing, it can be used in different scenarios for edge processing. So how dynamic data offloading is happening. First, the initial data analysis is happening at the edge. Then it checks the current network load. If the current network load is low, then it forwards the data to the immediate fog servers. If the fog server is busy or it is handling huge amount of data, then the data is sent to other fog nodes or cloud based on the policy. So normally how this data offloading is happening means initially whatever data is produced by the sensors are directly given to the fog servers, which is closer to that edge device. So if the server is busy or it is handling huge amount of data, then it checks the bandwidth. Bandwidth of the fog server is checked. If it can process the data, then the raw data is transferred to the fog server. If the fog servers are handling too much of workload, then the network load is transferred to other fog devices or the cloud devices based on the policy shared among the fog servers. So if we are using federated learning, this federated learning use case can be used for privacy preservation and model updates and global intelligence. The next research topic is we can integrate blockchain in edge and fog computing for more trust, because in blockchain we use immutable ledgers for secure transaction between devices. Once the block is created, it cannot be modified or deleted at any circumstances. So we for providing decentralized trust, we can go with this blockchain technologies, and it ensures the authenticity and unalterability of IoT data. So even a small amount of change in the raw data will produce different insights or different decision making in the fog and cloud servers. So if we are using blockchain in edge and fog computing, it provides decentralized trust and data integrity is there, because once the block is created, it cannot be deleted, removed, or changed under any circumstances. So for secure transactions, for example, if you are transferring the local updates from the fog server to the cloud server, or the cloud server is producing the global insight that is shared with the fog nodes and the edge devices, for securing this type of transactions, we can go with this blockchain technologies. So by using this, we can increase the reliability and security, end-to-end encryption for data protection, secure boot process to prevent tampering, advanced intrusion detection, and fogging. Then other research opportunities are security and privacy at the edge, energy efficient fog architecture, and hybrid orchestration. So because in edge and fog, most of the research are focusing on security and privacy, load balancing, and energy efficient architecture, hybrid orchestration, how seamless integration of this cloud, fog, and edge can be carried out. How can we provide this access control? How we can transfer the workload from one fog server to another fog server? How load balancing is happening? How dynamic load balancing, dynamic scheduling? All these are the recent research areas in fog and cloud computing. Then the research gaps. So in current industry trends, we have to analyze the importance of fog and cloud computing in the context of real-time applications. And for moving towards and transferring data, we need 5G integration. Then now the 5G network is implemented for secure data transferring between the devices and cloud. Now it's moving towards 6G, and now SDG goals are also playing an important role in the industry IoT implementation. So we are moving towards these green energy aware federated learning and IoT latency benchmarks. So these are the open research gaps in IIoT, end-to-end IIoT latency benchmark, energy aware federated learning, explainability at the edge, resilient orchestration under fault conditions. Now this quantum and HPC are integrated at the edge. So by converging the quantum computing and high performance computing with edge and fog infrastructure presents a transformative paradigm for solving intractable industrial optimizations problem. So even though the fog and cloud integration is beneficial, most of the industrial integrations are under research only. Some of the companies only are moving forward the integration of cloud and fog with edge. But in most of the applications, still this fog and edge implementation is in research only. Then sustainability in IIoT. So green edge means in IIoT employment, the energy footprint of edge computing becomes a critical concern. So while implementing the edge computing, we have to focus on the energy efficiency. So power hour scheduling and dynamic voltage and frequency scaling, deployment of renewable backend micro data centers, intelligent workload shifting to cooler times or regions. So even we are implementing fog and cloud. If we are considering about green edge and sustainability, it's under developing stage only. So we have to focus on the energy efficiency and the renewable backed micro data centers and intelligent shifting of coolest things. So we have to focus on the sustainable development with fog and cloud computing integration. So skill development for the future of computing. Here, IoT integration, cloud native development, and edge deployment are the key areas to focus for faster, robust capabilities in edge and fog computing. So in this session, we have focused on the edge, fog, and cloud computing architectures that are suitable for industrial IoT systems. By combining all these layers together, we can deliver a safe, efficient, and scalable Industry 4.0 systems. So that's all. If you have any questions, you can ask now.
Participants, if you have any queries, please ask.
Ma'am, I have a question, ma'am.
Yeah, yes, ma'am.
In case of an edge, in case of a cloud computing, we are securing in terms of a blockchain technology. Like it's useful for it is used for an privacy purpose, like right, ma'am. So for
Yes,
an
ma'am.
edge computing and fog computing, what type of security? I mean, what type of technology which is given for an security?
Actually, in cloud and fog computing, basically we are not sharing the raw data. So if you are considering about edge computing, the sensors are directly sending all the raw data it collects to the cloud server. So we have to focus more on securing the raw data itself. But in fog and edge computing, we are not transferring the raw data from the patient directly. We are providing the local analytics and the local results only. The insights or the results, whatever is obtained from the raw data, only is transferred between different fog servers or cloud servers. So, focusing on the security of raw data is not there, but we have to focus only on the local updates or the sharing of intermediate results only. So whatever techniques we are implementing in cloud can be implemented in fog also, because in edge devices are resource constraints. We cannot implement all the things in the edge. But if we are using fog, we can integrate all the security measures, whatever is implemented in cloud in fog also, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Okay, ma'am. Any other questions, ma'am? Actually, this fog and cloud computing is evolving for last many years, but it comes into picture and comes into play when this integration, automation or integration of all these techniques like AI, machine learning, deep learning, edge computing, fog computing, cloud computing, all these integration comes to play when this industry 4.0 is introduced because automation is there. So instead of processing all the data with the use of cloud servers, we are moving towards the edge where the data is being generated.
Thank you, ma'am.
Okay, ma'am.
Okay. We extend our heartfelt gratitude to you for your insightful and enriching session. We truly appreciate the time and effort you dedicated to making this session impactful. Thank you once again for sharing your knowledge and inspiring our participants. Thank you, ma'am.
Okay, ma'am. Thank you, ma'am.
Thank you, ma'am. Participants, feedback link now available in chat box. Once you fill the feedback and leave the session. Okay, thank you. Jasmine, ma'am.
Yes, ma'am. If a photo can be taken, if
Okay,
time,
ma'am. Participants, please switch on the camera for 5 minutes.
Hello, ma'am. Hello, Mangai, ma'am.
yes,
சொல்லுங்க மேம்.
Ma'am, host has disabled your video. வருது, ma'am.
என்ன மேம்?
You cannot start your video because the host has disabled it. வருது, ma'am.
இங்க எங்களுக்கு கரெக்டா தான் மேம் வியூ ஆகுது.
yes, ma'am. Then, if you are not able to start the video, no issues, ma'am. You have taken. Thank you all.
Thank you.
Assistant Professor Parikada. Name the institute. Technology.